Hi everyone. So welcome to lecture number 10 of Counting. So we are doing Data Science and Artificial Intelligence complete GATE course, and this is lecture number 10. In the last lecture we already saw how inclusion and exclusion principle works. In this lecture we are going to see a few problems on inclusion and exclusion, so as to get used to the formula, and we will apply it with various techniques that we have seen so far, like combination with repetition, permutation with repetition, and so on. So just to revise, in the general form, if we have n sets, then this is what the principle of inclusion-exclusion looks like. So the cardinality of union of n sets, a1 union a2 union a3 up to an, is sum of the individual cardinalities taken one at a time minus sum of the cardinalities of intersection taken two at a time, then plus the cardinalities of the sets, their intersection taken three at a time, and so on up to n at a time. So we will have like plus or minus n whatever depending on minus 1 to the power n minus 1, and all taken all at a time. So this is what inclusion exclusion principle is. I have explained this in lecture number 9, so you can watch that video if you haven't. So let's see a few problems. So this is the first problem. Always try to solve the problem, pause the video and solve it on your own. So how many permutations of 26 small case English alphabets do we have that do not have cat, dog or mule as a substring? See, there are various terms written in this problem. First is how many permutations of 26 small case English alphabets are there. So permutation means arrangements, we know. So we have 26 small case alphabets A, B, C up to Z. How many different permutations are there of 26 alphabets? 26 factorial. This goes way back to the first or second lecture, right? So we can arrange them in 26 factorial ways. For the first position we will have 26 options, then for the second position we will have 25 options, and so on. That's how we derive factorial, right? There are 26 factorial total permutations of all the basically letters of English alphabet. Now we just want all such permutations which do not have cat, dog or mule as substring. So like what is a string? Like let's say this is a string, right? Like this is a string, right? And here like BAN is a substring of this string. So substring means continuous string which is a part of this string. So like BAN is a substring of this string. So like when we create any permutation of all the letters from A to Z, when we create a permutation, let's say A, B, C, blah blah blah, let's say you can have Q, R, S, T. This is also a permutation like A to Z. You can write them in reversed order. Like there can be many such permutations, but some of them will have C, A, T in that order, right? And you can have like other alphabets here. So this is one such string. It can have CAT in the middle somewhere, or it can start with CAT. It can have cat, and it can have cat and dog both as well as the substring. Since see, cat, dog, CAT, DOG and MULE, these are all animals and they don't have any character in common. Basically, you can have cat and dog both as a substring of a string, right? You can have a string like this. You can have a string like CAT, it has a CAT, it has a dog, and it can also have mule in the same string. So you can have MULE as well, and you have remaining characters here and there. Blah blah blah. Okay, so this can be one such string. So it has like all three, cat, dog and mule in it. Since they don't have anything in common, it is quite possible that you can have all three as the substring of the string as well. So what we want is now, so we will apply the principle of inclusion-exclusion here. We know that there are 26 factorial total permutations. Right? So we will subtract all those which have cat as a substring. So if you have to have cat as a substring, I already told you how to solve this problem. So consider CAT cat as a single word. Consider CAT cat as a single word and all other characters as different letters. So how many total letters now you have? So 26 minus 3, 23 we have here, plus 124. Total 24 letters we will have. Considering CAT as a single letter, then we will have 24 letters and we can arrange them in 24 factorial ways. So there are 24 factorial ways in which cat will be present as a single letter. Similarly, we will subtract all those with dog as a substring. So all the permutations in which dog is a substring, again there will be 24 factorial, since dog is also of length 3, same way. And again we will subtract all those which have mule as a substring. So for mule to be a substring, consider mule to be a single letter and consider all other characters to be different letters. So how many we will have here? 22 we will have here and 23. So 23 factorial. So we subtract all those having cat as substring, dog as substring and mule as substring. Then we will add all the combinations in which we have both cat and dog as substring. So both cat and dog as substring. So it means we have to consider cat as a single letter and we have to consider dog as a single letter, because cat and dog will always come together. And then how many letters are remaining? So 1, 2, 3, 4, 5, 6 are gone. So 20 more are there. So 20 plus 1, 21 and plus 1, 22. 22 different letters are there, considering cat as one word and dog as one letter. So 22 factorial. Right? And then similarly we will add all those combinations in which we have cat and mule together. So for cat and mule to be together, so 7 are gone, 19 more are there, so 19 and then 21. Okay? And then again we will add all those combinations in which, all those permutations in which dog and mule are together. Again it will be 21 factorial, you can check. Okay? So this is taken like 0 at a time, then 1 at a time, then added 2 at a time. Then now we will subtract all 3 at a time. So from this we will subtract all the permutations. From this we will subtract all the permutations in which we have all 3, which means cat, dog and mule, all 3 as a substring. So consider this as a single letter, consider this as a single letter, consider this as a single letter. Consider them G1, G2, G3. Then how many other alphabets are left? 10 are gone, so 16 are left. So 16 plus 1, 17, 18 and 19. So we have 19 factorial such combinations in which all the 3 come as a substring. So these many possibilities are there. You can take 19 factorial common and do some math, but it is not required. This is your answer, like 26 factorial minus 2 times 24 factorial minus 23 factorial and so on. Okay, this is your answer. Cool. Let's move to the next problem. So yeah, in how many ways can the letters A, B, B, C, C, D, D be arranged such that no 2 consecutive characters are same? Okay. So firstly we can see like in how many ways can we arrange these characters. There are 8 characters given, 2 A's, 2 B's, 2 C's and 2 D's. In how many ways can I arrange these characters? So it is like we have 8 different letters. So 8 factorial upon, I told you, like see, since A and A are together, first consider them different, A1, A2. So how do I do that? If like since we are over counting every 8 twice, you have to divide by 2 factorial. Then for B also 2 factorial, for C also 2 factorial, for D also 2 factorial. We are over counting every permutation these many times. So this is our answer if all the letters, like if there is no condition given. And this is the number of ways in which we can arrange A, B, B, C, C, D, D. Right? We already have seen this in previous videos, you can watch the video. And now we have a condition. So that condition is which makes this problem inclusion-exclusion. So such that no 2 consecutive characters are same. It means that A and A cannot come together. Both A's cannot come together. See, in these permutations it will be possible that they are coming together. So like it has to be something like this: A, B, C, A, D, C, D, B. It can be something like this. Here no 2 consecutive characters are same, right? So basically both A's, both B's, both C's, both D's cannot come together. So again, like let's apply inclusion-exclusion. We know that the total number of possible permutations here are 8 factorial upon 2 factorial, 2 factorial, 2 factorial, 2 factorial. This is total number of arrangements of A, B, B, C, C, D, D. Okay. Now we have to subtract all the cases in which both the A's come together. So right now I'm only taking all the cases in which A's come together. Right. Similarly, we will have B's come together. So like it's a set. Like we have 4 sets here: A, B, C, and D. A come together, B come together, C come together, and D come together. Right. And there are a few cases in which all of them come together as well. So one such string is A, B, B, C, C, D, D. So here all the consecutive characters are coming together. Right. Like the same characters. So what we will do, we will subtract all the cases in which both the A's are together, which means we have to consider this as a single letter. So how many letters we have? 1, 2, 3, 4, 5, 6, 7. 7 letters are there, 7 factorial ways, and here there is some repetition. So B is coming twice, C is coming twice, and D is coming twice. Both A is a single letter anyway. So we will have 2 factorial, 2 factorial, 2 factorial for B, C, and D. So let me write it in a compact way. So the total number of initial ways was 8 factorial upon 2 factorial to the power 4. This is total permutations. I will subtract all those in which both the A's come together, which means 7 factorial upon 2 factorial cube. This is the total number of ways in which both the A's come together. And also similarly for both the B's, B, C, and D, the number of ways will be same. You can consider both B's to be together, then the number of ways will be same only. So this will be subtracted 4 times. For A, either A's are coming together or B's or C's or D's. Basically the cardinality of A coming together, B, C, and D are same, right? So like this will be subtracted 4 times. Now we will add the cardinality of A intersection B, which means A is also coming together and B is also coming together. So it means A is considered as a single letter, B is also considered as a single letter. Then we have 2 C's and 2 D's. So total 6 letters are there, 6 factorial upon 2 factorial for C, 2 factorial for D, and these are individual letters. So these many 6 factorial upon 2 factorial, 2 factorial, or I should write it in like this: 6 factorial upon 2 factorial square. This is the number of ways in which both A and B come together. Now we have to add this for all possible pairs: A and B, B and C, C and D, A and C, A and D, and C and D, right? So we have 4C2. We have 4C2 such combinations, which means like 2 at a time. From the 4 sets, if I want to take 2 at a time, we have 4C2 combinations. For all those 4C2 combinations, we are taking 2 at a time, and the number of cases is same: 6 factorial upon 2 factorial square, right? So this is like taking 1 at a time. This is taking 2 at a time. Then we have to subtract all those in which we are taking 3 at a time. The number of such triplets will be 4C3, which means A, B, C are coming together, A, B, D, B, C, D. So these are the 4 cases, right? A, B, C, A, B, D, A, C, D, and B, C, D. So consider any one of them. So if A and B, A is considered a single letter, B is considered a single letter, C is considered a single letter, total number of letters we have is 1, 2, 3, 4, 5. So 5 factorial upon 2 factorial. So this is 5 factorial upon 2 factorial. Then finally we will add that one case in which all of them come together: A, B, C, and D. All of them come together. There is only one such case, 4C4. And how many ways can we do? Can we arrange them? So like all of them are single letters. So there are 4 factorial ways. So this is the number of ways in which you can solve this. We can calculate it. Okay, it will come out to be 864. You can do the math. So there are 864 such permutations possible. Okay, so consider this next question. So what is the number of integral solutions to the following system of equations? X plus y plus z is 18. X has to be between 1 and 6. Y has to be between 2 and 5, and z has to be between 3 and 7. So this includes all the concepts that we have seen so far. Okay, combination with repetition and inclusion exclusion. So how to solve this problem? So we have this equation: x plus y plus z is equal to 18. Now the condition given is x has to be between 1 and 6, y has to be between 2 and 5, and z has to be between 3 and 7. Okay, so Okay, so we know that how to handle the left hand side of the solution equation, right? If x has to be at least 1, we will give 1 to the x. If y has to be at least 2, we will give 2 to y. And if z is less than has to be at least 3, we will give at least 3 to z. So basically we will write x as 1 plus a, and we will write y as 2 plus b, and we will write z as 3 plus c. Right? So what will happen? This equation will become a plus b plus c is equal to 12, and the condition here will become 0 is less than equal to a is less than equal to, so basically subtract 1 from all the sides. A has to be between 1 and 5, and b here has to be between 0 and subtract 2 from both the sides. B has to be between 0 and 3, and c has to be between 0 and 4. Right? Now we know how to solve this equation if right hand side condition is not there. So if a, b and c have to be greater than or equal to 0, we know that the number of solutions to this equation is 14c2 from combination with repetition, right? So let's forget about this equation now. We just have this equation. We already have merged this equation to this. Okay, we just have to solve this system of equations. Okay, we know that the total number of solutions to this equation is 14c2 if there are no conditions. Right? So we will subtract all the solutions in which one of the conditions is failing. One condition is failing. So let's take a condition. If this condition has to fail, a has to be greater than or equal to 6. If I don't care about b and c right now. A has to be greater than or equal to 6. So if only a is greater than or equal to 6, the total number of solutions will become what? Again, like write a as 6 plus p. Okay, it will become easier. Like once you do more and more problems, write a as p plus 6. So this will become p plus b plus c is equal to 12 minus 6. This is 6. So there are 8 c2 ways in which a is greater than or equal to 6. Similarly, we have to subtract all the cases in which b is failing the condition. So now we don't care about a, we only care about b. So basically b is greater than or equal to 4. So there are 9 c2 such ways. Okay, so b is greater than or equal to 4. So write b as p plus 4. So write b as p plus 4. So the equation becomes a plus b plus c is equal to 8, and the number of solution is 8 plus 2, 10 c2. Here b is greater than or equal to 4. Okay. Similarly, we will subtract all the cases in which c is failing its case, which means c is greater than or equal to 5. Right? So if c is greater than or equal to 5, the equation becomes a plus b plus p is equal to 7. Right? So the number of solutions is 9c2. C is greater than or equal to 5. Now we will add all the cases in which two of the conditions are failing. So let's say now we will add all the cases in which a is also greater than or equal to 6 and b is also greater than or equal to 4. Both the conditions are failing, which means I have to write a as p plus 6 and b as q plus 4, which means p plus 6 plus q plus 4 plus c is equal to 12, which means p plus q plus c is equal to what? 2. And the number of solutions to this equation is what? 4c2. Right? So we will add all the cases in which a is also failing its case and b is also failing its case. Right? Similarly, we will add all the cases in which a is also greater than or equal to 6 and c is also greater than or equal to 5. So this will become 3c2. And similarly, we will add all the cases in which b is greater than or equal to 4 and c is greater than or equal to 5. So we have 9 here, so it will become 5c2. And finally, we will subtract, see, inclusion, exclusion, inclusion, exclusion. We will subtract all the cases in which all the three conditions are failing, which means a is greater than or equal to 6 and b is greater than or equal to 4 and c is greater than or equal to 5. Is it even possible? It is not possible, right? If all the three conditions are failing, the sum cannot be 12. The least amount of sum is 15, so this becomes 0. There are no cases here. So you can try solving it and this will come out to be 1, okay? there is only one solution to this equation. You can solve this, okay? So this is lack of thinking clearly. If you directly jump to the problem, this might happen. But still you will get the answer. This will come out to be 1, okay? But if you see the constraint really carefully, since x has to be less than equal to 6 and y has to be less than equal to 5 and z has to be less than equal to 7, the only solution to this question is x equal to 6, y equal to 5 and z is equal to 7. Since their sum is 18. Right? So the only solution was 6, 5, 7. But yeah, if you apply the formula and apply inclusion-exclusion, you will get the same result. There is only one solution to this equation. Cool. And there is one more application to inclusion-exclusion formula, which is the number of onto functions possible from set A to set B. Okay. So if you consider two sets A and B, A contains n elements and B contains m elements. So what is the function? It is a mapping from one element of A to one element of B. Okay. This is a function. So I will make a separate video on all possible questions on functions, like number of functions, number of unknown functions, onto functions, bijections, surjections. I'll make a separate video on it, and it involves counting as well, since it is all PNC. So I will make one separate video on all the questions on functions and how it is linked to PNC. But for now, if you have to count the number of onto functions from set A to set B, it involves inclusion-exclusion principle. How? What is an onto function? So just consider this. An onto function is a function in which there cannot be any element left in codomain. Basically, range has to be equal to codomain. So this element cannot be left. There should be at least one mapping. There should be at least one mapping for every element in set B to set A. So what does it mean? This is not allowed. This element cannot be left empty. So one such thing is we already know m has to be less than equal to n. Then only this is possible. First thing. Right, if m is greater than n, it is not even possible, because you will have more elements here and some elements will remain empty. So there should be at least one pre-image of every element in B. That is what an onto function is. So again, you can use the inclusion-exclusion formula to solve this. So if you have this as set A and this is set B, this contains m elements and this contains n elements. So the total number of functions from A to B is what? M to the power n. How? See, for every element in the first set we have m options. For every element in the first set we have m options. It can map to anything. Right now we don't have any conditions. So total number of functions possible is m to the power n. For every element in the first set you have m different options. It can map to anything. So you have m to the power n options. Minus all the cases in which one of the elements has no pre-image. If this element does not have any pre-image, then every element here has to map to the remaining m minus 1 elements. So every element will have only m minus 1 options. So m minus 1 to the power n. And how many such cases are there? MC1 such cases are there. There are MC1 cases in which only one of the element remains empty. Similarly, we will add all the cases in which two of the elements don't have pre-image. So we choose two elements in MC2 such cases. And if two elements don't have any pre-image, all the elements have to map to the remaining m minus 2 elements, and so on. So we can apply the inclusion-exclusion formula to calculate the number of onto functions from set A to set B, and this will be the formula. So these are a few use cases of inclusion-exclusion principle. So we have seen permutation, combination without repetition first, factorial, and then permutation, combination with repetition, a few examples. Binomial multinomial theorem and its motivation, like how it links with combinatorics. Then we saw inclusion-exclusion formula and we solved a few problems. The few topics which are left in PNC are seating arrangement, circular arrangement and D arrangements, which we will see in future lectures. And also I will host a few practice problem sessions and doubt solving sessions. You can attend those and ask your doubts. Also do keep commenting your doubts on every lecture that you have. I'll keep responding to those. Thank you. Bye.